Hello, Math 111 students, and welcome to section 6.5, Logarithmic Properties. All right, in this section, we're going to talk about how to use the properties of logarithms, how to expand logarithmic expressions, how to condense logarithmic expressions, and how to use the change of base formula for logarithms. As we go through this, let's all make our best effort to remember to use parentheses when we write logarithms. That way we won't get confused about what we're taking the logarithm of. All right, let's go ahead and get started. This first page is really a reference sheet for you. I'm going to go through each of these properties one by one with examples, so I'm not going to read through them now, but this is a really great place to look for all the properties of logarithms in one place. Let's go ahead and get started. The very first property we're going to talk about is using the definition-based properties of logarithms. Let's look at these different definition-based properties and see if we can make sense of them using what we know about logarithms. The first example here says log base b of 1 equals 0. Let's rewrite this in its exponential form to see if this makes some sense to us. Remember, exponential form has the same base, so the base is b. b to the 0 equals 1. Well, that makes sense when you write it in exponential form because we know anything to the 0 is 1. So when we translate that back to logarithms, it means whenever we take the logarithm of any base of 1, we're always going to get 0. Let's look at the second one and rewrite it in its exponential form. It says that b to the 1 is b. So if you ever take a logarithm base b of the same base, it's always going to be 1 because that's the power you raise it to get back to itself. And the final example, let's rewrite this in its exponential form. b to the m equals b to the m. All right, so base to the m equals b to the m. And that makes sense, hopefully, to everyone as well. Let's use these properties to try these practice problems. I'm going to go ahead and erase this so I can indicate which property I'm using a little bit more clearly. All right, let's look at the first one, log of 10. Remember, if it doesn't say anything, it means log base 10. 10 to the what is 10? That's going to be number 2 property here, right? That's always 1 because 10 to the 1 is 10. B says log base 22 of 1. That's this property up here, right? 22 to the what is 1? 22 to the 0. Why don't you guys try C, D, and E right now? Pause the video and give them a try, and we'll come back and do them together in just a minute. All right, did you try those 3 examples? Let's see if we can figure them out together. Remember, natural log is base E, so here we're asking E to the what is E, and the answer is 1. So that's the first, the second property again. Log base 3 of 27. Well, maybe this will be a little more helpful if we write 27 as 3 cubed, and then we can see this is property number 3. Log base 3 of 3 to the 3 is equal to 3. That's a lot of 3's, but we know that 3 to the 3 is 3 to the 3. Finally, log base 2, 64 is a power of 2. I think it's 2 to the 6th. Yeah, it is, 2 to the 6th. 2 to the what equals 2 to the 6th? The answer is 6. I really like these definition-based properties of logarithms because I don't have to memorize them. If I rewrite it in exponential form, I can figure out the answer anyway, and I don't like memorizing things very much. All right, let's try our next property that we're going to talk about, and that's the change of base formula. The change of base formula is really handy when you're solving story problems that involve logarithms because it lets you get a decimal approximation for logarithms that are bases other than e and 10. We all know that you can use a calculator with the natural log button to use log base e, or just the log button for base 10, but let's say we wanted to compute this first one here, log base 2 of 21. Well, we know it's more than 5 because 2 to the 5, oh no, it's less than 5. We know it's more than 4 because 2 to the 4 is 16. We know it's less than 5 because 2 to the 5 is 32, but we don't know what it is. So we're going to use a change of base formula to help our calculator to get an approximation. Let's switch this to base 10, okay? So the change of base formula says if you have log base b of m and you want to switch it to log base a, the m stays the same as the argument in the numerator, and in the denominator you take the new logarithm base a of the old base. So let's plug this in with let's do a practice problem with this one for 10. So let's switch it to log base 10. So my new log is base 10. I'll write the 10 in just to be clear this time, but you don't have to write it. The m is what I take of the numerator, so log base 10 of 21. And the 2 is what I take the logarithm of in the denominator, so log base 10 of 2. Now I can use my calculator to approximate these. let's see, log of 21 is about 1.32, and log base 10 of 2, log 2, is about 0.30. If I take 1.32 and I divide it by 0.30, I get 4.4. And actually, I should have put the squiggles right there. All right, pause the video and try to use your calculator to approximate log base 7 of 37 by switching it to log base 10. All right, did you get log, and I'm not going to write the base 10 this time, I'm just writing log of 37 over log of 7. Log of 37 is about 1.57, and log of 7 is about 0.85. So 1.57 divided by 0.85 is about 1.85. So 7 to the 1.85 is 37. And if we kind of just sit and think about that, that makes sense because we know 7 squared is 49. So it shouldn't be as big as 2, and 7 to the 1 is just 7. So we know it should be closer to 2. All right, we can do this sometimes even to help us solve equations. So let's look at this example here. In part B, we're going to use this change of base formula from right to left instead of from left to right. And the farther you get along in math, the more you'll come across these situations where you use formulas both ways. And it really depends on the context of the situation if you're going to go from left to right or right to left. In part A, we took one logarithm and we made it into 2 to help us get approximations. Now we're taking 2 logarithms and we're going to put it back into 1. All right, so if we look at this the other way, this would be log, the base was in the numerator, base 3 of w, and that's another way we could rewrite this logarithm. Likewise for this one, if we want to switch this back to, I'm kind of confused about why it would be log base 5 of 5. What did I come up with? I'm trying to remember why I did this example right now. My brain's a little tired. Well, let's just do it. Log base 5 of v plus 2, which isn't super helpful because we are already log base 5, and we all know that log base 5 of 5 is 1. It's not the world's best example. Let's move on. Alrighty. Let's talk about the product property of logarithms. So let's recall the product property of exponents, and maybe that'll help us with the product property of logarithms. If we have b to the m times b to the n, we get b to the m plus n. So this is like if we had x squared and we multiplied it by like x to the 5th, right? We would get x to the 7th. That's what we're talking about here. Since logarithms are just exponents, there is a corresponding property for logarithms. The log of m times n equals log base b of m plus log base b of n. And if you look at the exponents on our exponent property, that's really what we're talking about. Let's use this property to expand logarithms. All right? So we're going to use this property to expand one log into multiple logs. Let's look at the first example. The first example says log base 8 of 13 times 7. Well, we can rewrite this as log base 8 of 13 plus log base 8 of 7. All right, let's try the next one. This is log base 9 of 9 plus log base 9 of t. Now this one we can simplify even more because we know what log base 9 of 9 is. 9 to the 1 equals 9. So this becomes 1 plus log base 9 of t. And you can see that maybe that's a little bit simpler. Why don't you try the next three on your own. Pause the video now and try these 3 examples. All right, let's go over C. We have a product of 10,000 times W. Sorry, that's my dog shaking his collar in the background. Log base 10 of 10,000. 1, 2, 3, 4. Yeah, 1, 2. Plus log base 10 of W. Well, what is 10? What power do you raise 10 to get 10,000? And the answer is 4. plus log base 10 of w. So we can just write it as 4 plus log w. All right, this one doesn't look like a product right away, but maybe you realize that you could factor this. Natural log of, let's see, we need two numbers that multiply to negative 12 and add to negative 4. So I'm going to go with v minus 6, v plus 2. Does that work? V squared plus 2v minus 6v minus 4v minus 12. Now we have a product, and we can write this as natural log of v minus 6 plus natural log of v plus 2. I'm so glad my dog can be here in the background for you guys. And finally, one more. Let's look at this one. This one already has two logarithms. Can we make it into one? This is an example, another example of what I talked about before, about using a formula from right to left in addition of using it from left to right. So if we look here, we can see we have log base c for both of these. Now we can rewrite this as a single logarithm by saying log base c of w plus 3 times d. And that's an example of condensing logarithms using the product property of logarithms. This is the end of video 1. I'll go on to talk about the subtraction property of logarithms or the quotient property of logarithms in the next video.